So, welcome. We are going to discuss bobbin speed regulations. Let us look at this slide first. As the roving delivery speed is constant, the flyer rotational speed is to be kept constant, since we have to keep the twist constant. So, we cannot change the speed of the flyer, because twist has to remain constant and the roving delivery speed is also constant. The other thing what we do during the roving bobbin formation is the roving is laid on bobbin in the form of layer, and bobbin diameter remains constant till a complete layer is formed. So, once we start building a particular layer, from that time onwards till that particular layer is completely formed, the speed of the bobbin should remain constant, it should not change. So, from beginning to end of a particular layer formation, the bobbin speed is not going to change. However, as the bobbin diameter increases, as you lay one layer and then we put the second layer and third layer, diameter keeps on increasing, and therefore, we need to reduce the bobbin speed in order to keep the winding speed same always, because the delivery is fixed and whatever is being delivered, the same amount of roving we have to always wind. So, winding rate is same, but the winding speed is different, because the bobbin is growing in diameter. So, the change in bobbin speed is brought about by using a variable drive, and we are going to discuss this drive now. A typical drive mechanism is shown in this particular slide. What we see here in this slide, if we look at this slide carefully, is that there is a central shaft. This particular shaft, we call it main shaft, and this shaft gets its drive from the motor through a set of gears or maybe pulleys, and speed of this shaft is always fixed and constant. This shaft rotates as a constant speed, and from this shaft, if you trace the motion transmission, then we see that from this shaft the orange arrow shows how the motion is transmitted, and the blue arrows also shows how the motion is transmitted. Now, if you look at the blue arrows, then the other end of the main shaft, there is a gear here, and from this gear the motion goes to the cone drum. So, there we have a top cone drum, and then we have another drum at the bottom, we call it bottom cone drum, and these two cone drums are connected by a belt. Then from the bottom cone drum, if we now look at the motion and follow the red arrows, you see that it goes through a set of gears to a differential gear. The differential gear is shown here, which consists of a housing, and there are 4 set of gears, and the output of the differential gear is from here, and which is going finally to the bobbin. So, the speed to the bobbin is a resultant of the speed that it receives from the cone drums, which is the variable part, and a speed that it receives from the main shaft, because the housing of the differential gear is also turning at the speed of the bottom cone drum, but the main gear here is rotating at the speed of the main shaft. So, we will see that the two speeds, one constant and one variable speeds, are being added together. We will understand this as we go through this lecture. If we remember the previous equation that we derived earlier, we have seen that the bobbin speed is Nb is V by pi dB plus Nf, and the winding speed, which is Nb minus Nf, is inversely proportional to the diameter of the bobbin. This we have already learned. Now, we move on to this slide. The variable speed is accomplished by a pair of conical drum, as we have seen in the previous slide, and which is connected by a common belt. As you see in this diagram, the belt is there. Depending on the requirement of the speed, the belt is shifted to change the diameter ratio of the drums. So, the belt position is not fixed, but it keeps on moving depending upon the requirement of speed. Since one drum, the driver drum, rotates at a constant speed, this driver drum rotates at a constant speed. The driven drum speed changes depending upon where the belt is located. Speed of the top drum, in this case the driver drum, is always fixed and constant. So, bottom drum speed will keep on changing depending upon the location of the belt. The speed ratio of the driven drum is then utilized, speed of the driven drum is utilized to drive the bobbin. So, the speed of the driven drum, in this case the bottom drum, keeps on changing depending upon the location of the belt, and this speed is then fed to the differential gear to change the speed of the bobbin. Now, one thing we should learn here, that is the cone drum profile. We have said that we need two drums, one at the top and one at the bottom. The top one is usually a driver drum and the bottom one is a driven drum. Now, what should be the exact profile of the cone drums? Now, the diagram is shown in the right hand side of the slide. At the end A, the radius of the driven cone is smaller than the driver cone. So, if you compare the diameter at the end A here and here, we see that the driven cone drum diameter is much smaller than the driver cone diameter, and if we compare it with the other end, it is just opposite, that at the end B, the driver drum diameter is much less in comparison to the driven drum. Now, the two cone drum profile must satisfy the following conditions. What are those conditions? Condition number 1 is, as the motion transmission is by a common belt, the radii of the two cones at any location should be such that the length of the belt required at any position must remain constant. See, we have to always use the same belt. So, as we move along the length of the cone drums, the belt position keeps on shifting, but since the length of the belt should remain constant, this we have to remember that whatever is the diameter ratio, whatever the diameters at that particular locations, the length of the belt should remain constant at any locations. The other thing is, the rate of change of speed ratio of the cone drums with position of the belt must satisfy some conditions imposed by the purpose for which the variable speed mechanism is required. The rate of change of speed ratio of the cone drums. So, as we move, the diameter ratio changes and therefore, speed ratio also will change, but it must satisfy some conditions. Now, what is that conditions? We will understand this. The cone must be so shaped that while the belt moves by y centimeter, see y is the length of the cone drum, parallel to the axis of the drum, the speed of the driven cone varies linearly, say from 50 to 200 rpm, while the speed of the driver drum being 100 rpm. Let us say that there is a condition where the driver drum will always rotate at the speed of 100 rpm. The bottom drum speed must change between 50 to 200 rpm, because that is the requirement, and that is from one end to the other end. The speed, if is the minimum speed to maximum speed in this case is 1:4. In one end I get a 50 rpm I must get, the other end as I go to the cone drum I should get a speed of 200. So, 200 by 50 gives you a value 4. That means, the minimum to maximum speed ratio is 1:4. That is what is also a part of the requirement, let us say. Now, why the speed of the driven cone drum varies linearly? It was stated earlier that the speed of the driven cone drum varies linearly from 50 to 200 rpm. The way we should design the profile, that the speed should change from 50 to 200 in a linear fashion. The question that arises, why it should be linear? Because the bobbin diameter increases linearly with successive roving layer formations. So, in this diagram what we are showing, that in one side on the x axis we have layer number, and on the y axis we have bobbin diameter. What we see here, that as we keep laying the layers, the diameter will increases in a linear manner. Here we are showing the way the diameter increases for 3 different roving fineness, 1.0 Ne, 1.4 Ne, 1.8 Ne. 1.8 Ne is much finer than 1.0 Ne, and therefore, the slope of the line is less in comparison to the one where the roving diameter is larger. The final diameter that we are attaining is constant here, whatever diameter we can set it, and let us say if that diameter remains constant, then the slope of the way the bobbin diameter is increasing will change depending upon the thickness of the roving, but the increase in diameter with layer number is linear in nature. Because this is linear, therefore, the speed ratio also has to be linear. Since the drums are far apart, it may be assumed that the angle of wrap of the belt around the cone is, let us say, same, and it equals to 180 degree. That is, it is going over this belt which is here is going over the driver and the driven, and the angle of wrap around the drums is, let us say, 180 degree. Therefore, the length of the belt, we can work it out, is going to be the distance between the center, see this distance is L. So, on both sides it is there, so it will be 2L plus the circumference around the top and the bottom. So, it is pi r1 plus r2, that becomes the actual length of the belt, where L value remains same, r1 and r2 keeps on changing depending upon where the belt is. L is therefore, L is always constant, that is center to center distance between the two drums. The other thing is, S also has to remain constant, where S is r1 plus r2, that is the summation of diameter or radius in this case of the two drums, that should remain constant, because the belt length has to be same. If the belt length has to be same, then in this case L is constant and hence pi is constant, and therefore, r1 plus r2, sum of r1 these two radii has to remain always same. Then only we can use the same belt for running the cone drums from one end to the other end of the drums. At any location of the belt surface, speeds of the two cones are actually same, because if I drive it by as if it is a pulley and there are two pulleys, one at the top, one at the bottom, and these two pulleys are connected by a belt, and if the top pulley is driving the bottom one, then what will happen? The surface speed will be constant, and if the surface speed is constant, then we can write that n1 2 pi r1 is going to be n2 2 pi r2, where n1 and n2 are the rotational speed of the respective pulleys. In this case, it is driver cone drum and driven cone drum. If they are same, from there we can write what is n2. N2 is basically becoming n1 into r1 by r2. This r1 by r2 is the ratio of the radius of driver and driven cone drum. We have written it as capital R. So, what we can write, n2 is equal to n1 into r. So, the ratio will decide the speed of the driven cone drum. N2 is the speed of the driven cone drum, n1 is fixed constant. So, n2 depends upon the exact ratio, that is r, capital R. So, we can say n2 will be changing linearly with r, because n2 equal to n1 into r. This is the equation of a straight line. n2 will vary linearly with r, therefore, n2 is proportional to r, where capital R indicates the ratio of the radii of driver and driven cone drum at any locations. Let us say our control requirement is such that the top cone drum, we just stated earlier, runs at a speed of 100 rpm. The bottom cone speed has to vary from 50 to 200 rpm. As the distance x of the belt from the point B varies from 0 to y centimeter. See, this distance x is shown here in the diagram. X we are measuring from the right hand end, that is from the end B. So, the distance of the belt from the end B is designated as x. So, the value of x could be theoretically 0 when the belt is on the extreme right hand side, and it could be up to y if it goes to the other end of the cone drum. So, theoretically that is the value of x at any given location. Let us say the distance from the end B is x, and the maximum value of x is going to be y, where y is the distance between the two ends of the belts as shown in the diagram. Now, for constant n1, because n1 is the speed of the driver cone drum, and this driver cone drum receives its speed from a main shaft which is connected to the motor, and therefore, the speed of the driver cone drum is always fixed and constant. So, what constant n1, n2 depends upon the radius ratio r, which we have shown earlier. To satisfy the speed requirement, r has to change, the ratio has to change from 0.5 to 2, because the speed has to change from 50 to 200. So, 1:4. Therefore, in this case the ratio of the drum diameters should vary from 0.5 to 2, and if we take the ratio of 2 and 0.5, we get a ratio of 1:4 again. So, this must change from 0.5 to 2 in a linear manner as x changes from 0 to y, because the maximum value of x is y and minimum is 0. So, if we look at the diagram here below, how r has to change, we are showing here that r is changing linearly from 0.5 to 2 as x is changing from 0 to y. So, as x changes from 0 to y, r should change from 0.5 to 2. Now, if we look at this graph which is shown here, we have to find out what is the equation of r. R as is shown here is a straight line and with an intercept which is 0.5, that is the starting value of capital R. Capital R indicates the ratio of the radius, or we can also say diameters of the two drums. So, what is this equation? It is a straight line equation. So, R is how much? 0.5, 0.5 is the intercept, and the other thing is how much is going to be the slope. Slope is going to be 1.5 by y. 1.5 by y is basically the slope of the line, and you multiply it by x to find out the r value at any position x. So, it is basically 0.5 plus 1.5 by y into x. 1.5 is basically from here to there is 1.5, and from here to there it is basically y, and therefore, if I want to find out this tan theta, the slope is going to be 2 minus 0.5, that is this value. This is 2 minus 0.5, that gives you 1.5, and from here to there this is actually y. Therefore, tan theta is going to be 1.5 by y. So, that is the slope that you multiplied by x to find out the value of r at any location. So, this equation is r, we should write 0.5 plus 1.5 into x by y. Small r 1 equal to s minus r 2, because some of them the s value is basically sum of the diameters or sum of the radius, it should remain constant. That is because we are using the same belt to drive. Therefore, r 1 is s minus r 2, where s is a constant, which is sum of the diameter or radius or diameters of the two drums. Substituting small r 1 in equation 4, r is small r 1 by r 2, because it is the ratio, and r 1 I replace it by capital S minus r 2, and we then therefore write that capital R is s by r 2 minus 1, which is equation number 5. So, equation number 5 and equation number previous equation number 3, both are equal to r. So, these two are actually same, hence s by small r 2 minus 1 is equal to 0.5, 1.5 by into x by y, because both of them are basically equal to r, they are equal to r. Now, once we have this, we go for simplification process now. I can write s by r 2 equal to 1.5 in plus 1.5 x by y, and that 1.5 we take common, and this becomes 1.5 into 1 plus x by y, and then from here we can write what is r 2. So, r 2 we can write easily this, therefore, it becomes s by 1.5 within bracket 1 plus x by y. By simplification we get the equation 6. So, this equation can give us the value of r 2 at any location x, provided we know what is the S value we have to decide in advance. What is should be the sum of diameters of the two drums? That can be decided, maybe it could be 8-inch and 12-inch combinations. So, that gives you total 20 inches. So, S becomes 20 in that case. Then Y is the length of the cone drum. So, length of the cone drum also we have to decide that it should be 2 feet or 2.5 feet, whatever it is we can decide, and so that has to be decided in advance. So, once we know S and Y, then X we will put the values starting from 1 centimeter, 2 centimeter, X will go from 0 to Y. So, for different values of X we can find out what is the corresponding values of R2, because S and Y are known to us in advance, and therefore, we can calculate R2 at different values of X. And once R2 is known for a particular value of X, we can find out what is the value of R1 also, because R1 is S minus R2. So, therefore, for any location X, we can find out what are the corresponding values of R1 and R2. We can find it out, and once we have the R1 R2 values at different location of X, we can now plot it on a graph paper, and we can easily find out. We can make the profile also, because we have the values of R1 and R2. We can draw a diagram showing the profile of the top cone drum or the bottom cone drum. Now, one more thing we have to decide, that is how much should be the cone drum length, that is Y. As I said that we can choose a value of 2 feet. So, 1 feet basically means 30 centimeter. So, 2 feet means roughly 60 centimeter. So, let us take an example and try to understand how much typically the value of Y could be. Y is the length of the cone drum. Okay. So, let us say the roving diameter dr is 1 millimeter. The roving diameter in compressed state is k dr, because the roving is a very soft material, and therefore, when I wind the roving on a bobbin, then it gets compressed, and from a circular cross section it changes to an elliptical cross sections. So, compressed state diameter will be little less than what the diameter one would expect when it is not really wound. Anyway, let us say there is a factor k, but for the time being we are assuming the factor k to be 1, and hence let us say the diameter of the roving in a compressed state is also equal to 1. So, bare bobbin diameter, let us say 5 centimeter, full bobbin diameter is 15 centimeter. So, layer thickness, if we try to calculate, then we will find it out. The layer thickness is going to be 15 minus 5 by 2, and which will give you 5 centimeter or 50 millimeter. So, if I take the cross section of a roving bobbin whose dimensions are 5 centimeter and 15 centimeters, then actually its thickness of the layer, combined thickness, will be around 50 mm. Therefore, how many layers we require? 50 by 1. Each diameter, each roving diameter is 1 millimeter. So, roughly we can say the number of layers will be 50 by 1, that is going to be 50 layers. It is not exactly actually 50, because it is just an assumption, and we will see that in an actual case it may not be exactly 50, but to make the case simple, we are saying the total thickness is 50, each layer is of 1 mm in diameter. So, therefore, we need 50 layers to get 50 millimeter thickness. Now, the belt shift per layer formation, you see we have to shift the belt, so that we get the right speed. This belt shift per layer formation should not be too narrow or not should be too wide. This is due to the limitation of shifting mechanism, which is purely mechanical in nature, and therefore, the typical shift per layer formation is around 10 to 12 mm. The belt shifts the way the mechanism works, which is basically a mechanical mechanism completely, that it shifts by roughly 10 to 12 millimeter per shift. So, number of shifts equal to number of layers. If there are 50 layers, I have to shift the belt 50 times. Therefore, total shift of the belt is going to be 50 into 12, that is 600 millimeter. Some part of the cone drum has to be left unused on both sides of the cone drum, so that the belt does not slip from the edges. So, from both sides a part is left out. We do not place the belt exactly on the edge, but there is a chance of slippage. So, we leave some portions from two edges, and which could be around 75 mm from both sides. So, 75 mm on the left hand side and 75 mm on the right hand side we generally leave, which is close to actually 3 inches. So, total belt or total cone drum length is going to be 75 plus 600. So, it is going to be 750 mm. So, we can roughly say that a typical length of the cone drum is going to be around 750 mm. It is close to that. It could be little less, little more, but this is a rough calculation to give you an idea that how much should be the length of the cone drum. Now, we will discuss this thing. The way we can find out the drum diameters, and if we then make the profile on a graph paper, we will see that the shape is hyperbolic in nature. So, these are called hyperbolic cones, but most of the modern machines have straight surface cones, not hyperbolic cones. Why? Hyperbolic cones are difficult to design. First of all, belt has to move on surfaces of varying inclinations. This is another problem, because hyperbolic cones, the inclination keeps on varying from place to place, and belt is shifted by always by a constant amount in this case. The advantage is that I have to shift the belt by a constant amount always. That is the advantage, but disadvantage is they are difficult to design, and the belt will be on varying inclination on the surface of the two cone drums. Whereas straight cone, as shown in the bottom right hand side bottom, are easy to design, but the only problem is the belt must be shifted in steps by varying magnitude in this case, because by the previous equations the diameter that we get, they give you a profile which is hyperbolic in nature. They do not give you a profile which is conical, and when you have gone, if you go for conical surface, then obviously the ratio, the diameter ratio will not be maintained from place to place. It will be different than what we should have it actually. So, to take care of this, what we have to do? We have to shift the belts in varying magnitude. Initial steps are to be larger and later on to be smaller. So, to shift the belt by varying amount, because then you have to shift it by non-linear manner. It is not that for every layer formation the shifting will be exact the same amount always. it will change, and we do it by having an eccentric, that basically by a small cam is there, and in the belt shifting mechanism you will see that there is a connecting cord, or we can say rope, which is actually passing over the eccentric or the cam, and as the cam turns or the eccentric turns, varying amount is released, and therefore, the belt shifting is not by constant amount, but by varying amount. Now, rotational motion integration we will discuss now. The mechanism part we have discussed. Now, how the two motions are getting integrated, we will discuss this point. Bobbin's piece has two components. Now, if we look at these equations, we see that Nb is Nf plus V by pi dB. Nf part is the constant part and V by pi dB is the variable part. That means, I can split the bobbin, motion of the bobbin or speed of the bobbin into two components. One is fixed component, another one is variable component. Constant, the variable components are integrated by a differential drive. So, what we do, that we generate a constant speed and we also generate a variable speed, and these two pieces are then integrated by a mechanism which we call differential gear. Constant component source is the main shaft as shown it in the diagram, and the variable component source is coming through the cone drums. So, that is how the system is working. So, therefore, because the bobbin has two sources of drive, one coming from the main source and the other coming from the variable source, and then these two speeds are, when they have to sum them up basically, then we take the help of variable speed drive, and that is what is known as here in this case differential gear. Then the differential drive, if we try to understand how the two motions are integrated. We are showing it the drive in this diagram now. First of all, we have to understand the epicyclic ratio. If you look at the drive here, see this green part is the constant component where the main shaft is there, and the main shaft is going through and through, and then on the main shaft there is a casing. Within the casing you see 4 set of gears A, B, C, D. This whole casing or the box along with these 4 set of gears, we call it differential gear. The differential gear, the output gear is the gear B, speed is L. See, gear B is the output gear, and this gear and 45T, this particular gear, they are actually connected, and these two are actually loose on the main shaft. So, the main shaft is running through and through, but the gear B is actually loose on it. The first gear is the gear A, and let us say speed is F. The gear A is here and the gear A is connected to the main shaft. So, gear A gets a speed which is the speed of the main shaft. In this case, the arm speed, casing is called the arm, because the gear A becomes basically a sun gear and the gear CD becomes a kind of planet gear, because the CD actually rotates around the periphery of A. And how it rotates? Because the casing is connected to the gear V, and V is receiving its motion from the cone drum. So, as V turns, the casing turns. As the casing turns, the gear CD also will turn, and it will turn around A. Therefore, the two motions, one from the main shaft and the other coming from the cone drum, these two are actually integrated within this chamber or the box which we call differential drive. And in this case, it can be shown that the epicyclic ratio is L minus A by F minus A. This proof we are not going to do it in this particular lecture. So, E is what? E is the epicyclic ratio, and E is in terms of it can be found out from the teeth ratio of gear A, B, C, D. So, it is basically A by C, where A and C indicates the respective teeth of the gear A, B, C, D. So, A, B, C, D in this case are also representing the number of teeth or number of tooth in the gears A, B, C, D. So, A is driving C, A and C are connected. So, it is A by C into D by B. This is how we should write it, and epicyclic ratio in this case is therefore A by C into D by B, where A, B, C, D represents the respective teeth in those gears. Also, it can be shown that E is small l minus A by F minus A, and therefore, from here L, the speed of the output gear, is A plus E into F minus A. Now, for a typical case, we can write that value of E is A by C into D by B. So, in this diagram, the values are given. A is 32, C is 16, D is 15, B is 33. We get a value this, and there is a sign plus here. The sign indicates what? Now, if we look at the A drives C, C and D drives B, if the directional rotation of A, that is the first gear within the differential gearbox, and the last gear in the differential gearbox, we have to compare in terms of their directional rotation. If I turn A clockwise and if we get B also turning in the clockwise direction, then we put a sign plus. However, if it is opposite, that when A turns clockwise, B turns anti-clockwise, then we will put a sign negative sign. So, epicyclic ratio in this case is plus 10 by 11. Let the central start speed be, as a typical speed we have chosen 705 rpm, and if I say there is no cone drum speed, this cone drum is not feeding any speed, let us say, just for the sake of calculation purpose, we can also add whatever speed it is feeding. So, therefore, whatever is coming from the gear of the that feeds speed to the differential, let us say that is 0. This is the gear V. So, speed of BV is 0. So, speed of the main shaft is not 0, it will be 705 rpm. So, from this formula E equal to L minus A by F minus A, we can write what is the value of A, 10, E is plus 10 by 11, and we put the respective values of A and F. In this case, L is what we need to find out, L is the speed of the output gear, and therefore, we can say L is 705 into 10 by 11, it gives you a figure 640.9. So, the gear B basically that means will turn at the speed of almost 641 rpm if the main shaft rotates at 705 rpm and there is no input from the cone drum. Otherwise, if there is some input from the cone drum, then we can put those values and we will be able to get the whatever speed we need. And when there is no speed being fed from the cone drum, then the speed of the gear, now from B the motion goes to 45 T wheel, from there it is going 32 and from there it is going to the flyer or to the bobbin depending upon what is connected to this. So, therefore, in this case speed of the gear B and 45 T are same, because they are both this speed of this speed are same, because they are on the same shaft. Therefore, speed of the bobbin is going to be 640.9 into 45 by 32 and 45 by 37, as the gears are shown here. That will give me the speed of the bobbin, and we get a speed of 1096 rpm. That could be the typical speed of the bobbin in this case. This is how we can calculate the speed of the bobbin. Belt shifting mechanism we are now going to discuss. Now, belt has to be shifted. What is the mechanism for it? Now, basically if we look at the driving part of the machine, then we will see that there is a ratchet wheel which is mounted on a shaft. We have to go to the bottom of the machine, and then we can see that there is a ratchet mounted on a axle, and this is what controls the movement of the belt. Now, if you look at this ratchet wheel moves by half tooth after each changeover of operations. See, if you look at this ratchet is connected by a wire which is shown by this blue line, and the blue line, then you see there is another mechanism, it is connected. There is a small wheel over here which is running over inclined plane, and then there is a belt guide, this plane, then from here there is a connection. Look at this orange line, and there is a dead weight hanging. This is, if you look at the mechanism, that these are the components which are here. The belt guide is here, and then the dead weight is actually constantly trying to pull the belt guide, because the dead weight which is hanging here, it is always trying to pull this. Now, what happens by gear train, change wheel and eccentric, the ratchet releases the wire rope and enables the belt guide to move to the right hand side. The force required for this movement is exerted by the dead weight that we have seen earlier. That dead weight is actually always trying to pull, the constant pull is there, but it is prevented from, basically there is a ratchet and pawl mechanism. The pawl actually does not allow the ratchet to turn, even though there is always a pull on it. Unless the ratchet turns, the belt guide will not be able to move, even though the pull is there, because from the other side the ratchet, the pawl which is connected to the ratchet is not allowing the ratchet to turn, and unless the ratchet turns, the belt will not move. The rate of increase in bobbin diameter depends upon the roving thickness, that is the roving hank. The belt must be shifted by corresponding steps. The amount of sheet is regulated by replacement of the ratchet wheel or by change gear. Now, if you look at the connection here, in this case it shows that the ratchet is here, these are the two pawls. At any time one of the pawl is engaging the ratchet and will not allow the ratchet to turn, even though there is a pull from the dead weight. So, at a certain interval of time we will see that one pawl will be disengaged, and by disengaging this, momentarily the ratchet is released and therefore, the belt shifts. So, belt shifting is because of the release of the ratchet. Now, belt shift can vary depending upon whether I am producing a thicker roving or I am producing a thinner roving. That means, even though the ratchet is released for a slight duration of time, Let us say I am releasing the ratchet for only 2 seconds by removing the ball from it. So, the ratchet will turn by certain degree during that time before the other ball comes and engage with it. So, there is a dwell time of, let us say, maybe 2-3 seconds for which the ratchet becomes free to rotate, and that is the time when the belt will shift. Now, the belt shifting has to be made to different extent depending upon the type of roving that I am making, whether I am making a thicker roving or thinner roving. If I make a thick roving, the layer thickness is going to be more, and therefore, I need to shift the belt by more amount. If the make a thinner roving, the layer thickness will be thinner, I have to shift the belt by a lesser amount. There has to be some other mechanism also which will control the extent of shift of the belt. So, you will also see that what we do, now we do it in this case by changing the ratchet wheel. Ratchet with fewer teeth means larger steps, or ratchet with larger number of teeth means actually fewer steps. In this case, it is the ratchet which is changed in order to take care of the steps by which the belt will shift, which in turn depends upon the diameter of the roving that we are making. So, now let us, from here we are going to nature of bobbin rail movement. Now, what are the requirements? Bobbin rail keeps traversing up and down, because I have to lay the roving from bottom to the top. So, for laying, the bobbin rail has to move up and down. Each coil must be placed adjacent to each other. Coils should neither overlap nor leave gaps between them. It was also discussed earlier. The shifting of roving laying point. The shifting of roving laying point is accomplished by moving the bobbin rail which carries the bobbin, because the feeding point of the roving is fixed, that is the pressure arm, that does not move. So, that remains constant at the same place always, and the bobbin keeps on traveling up and down. The rail is moved either by a lever or by rack and pinion. So, here now a diagram is shown here, the mechanism part. We can see the how the motion is transmitted to the bobbin rail. You see the bobbin rail, if you look at it, gets its drive. Look at this bottom diagram. From the bottom cone drum, the drive goes through a set of gears to the bobbin rail. Now, why bobbin rail is driven from the bottom cone drum? Why? Bottom cone drum speed is not fixed, it keeps on changing, because depending upon the location of the belt. That means, if I feed the drive from the bottom cone drum, that means the bobbin rail speed also is not constant, it must change. Why it should change? Now, if you remember this particular equation which we derived earlier, VBR is this. VBR is the velocity of a bobbin rail is small v by pi d into dr. That means, VBR needs to be changed as the bobbin diameter dB is increasing. So, speed of the bobbin rail cannot be constant, it must must change as the diameter of the bobbin grows, and that means it is inversely proportional to the diameter of the bobbin, and it is also proportional to the diameter of the roving. So, VBR, if I write VBR is directly proportional to dr, diameter of the roving, that means count of roving, and it is also is inversely proportional to diameter of the bobbin. Because it is inversely proportional to diameter of the bobbin, that means its speed throughout the bobbin building is not constant. and cannot remain constant. We have to keep reducing the speed as the bobbin grows in diameter, and that is why the drive to the bobbin rail is taken from the driven cone drum. Okay. So, that is why if you look at this drive from driven cone drums to set of gears, it is going and it is actually driving a small pulley with sprocket, and then there is a chain, it goes like this fixed here, and the chain as it grows, as this thing rotates, the chain is going to be wound on it, and therefore, the lever is there which is supporting the bobbin rail. So, the lever is fulcrum at one end, and at the other end it is supporting the bobbin rail, and at the middle we have another small wheel, and this chain which is there is going over it. So, chain is actually wound on this gear, and therefore, we shorten the chain length or we release the chain length, and therefore, the midpoint of the lever in this case moves up and down, and because it is supporting the bobbin rail will also move up and down. The other thing is roving tension during winding. Difference between bobbin surface speed and delivery rate is a factor which affects the roving tension. So, we are very much concerned about the roving tension, because if the tension is too much, the roving is going to break. If it does not break, it may get stretched. So, and roving is very weak. Therefore, we are very much concerned about maintaining the roving tension constant throughout the building of the bobbin. So, primarily what are the factors which affect roving tension? One is difference between bobbin surface speed and delivery rate, that these two is the first factors which is most important. Here there should not be too much of mismatch, otherwise if the bobbin surface speed is much higher than the delivery rate of roving, then what is going to happen? The roving is going to break. On the other extreme, if the bobbin surface speed is less than the delivery rate, then the roving is going to be loose. Basically the winding speed of the bobbin which will matter in this case, and that is, it is the surface speed difference, is not the surface speed of the bobbin, it is the difference between surface speed of the bobbin and the flyer that actually does the winding job. So, the winding speed has to be equal to delivery rate. If it is more, it is going to break. If it is less, the roving will be not wound properly, it will be loose. Angle of wrap of roving around the flyer is another important point which affects the roving tension. For soft twisted roving, the roving does not wrap around the top at all. However, it may lead to false draft in the unsupported part of the roving. This you have to know that while soft twisted roving, this is what we do generally, though there is a danger of false draft, means basically stretch. For normal and hard twisted roving, a wrap of 180 degree is provided. A wrap of 180 degree is provided so as to adjust the tension in the roving. So that I get finally I get a bobbin which is neither too soft not too hard. Hardness of the package depends upon the winding tension of the bobbin, which in turn depends also on these things. If you see here, the pressure arms are shown, and the roving as it exit the hollow end of the flyer, it takes few wraps around the pressure. So, number of wrapping is also important, because more wraps means more resistance to the pull of the roving, and therefore, there will be more tension in the roving. And method of threading the roving on the flyer top, both will also affect the winding tension. So, because the more the path of the roving, as we create more and more obstruction and we create a path where it is not a straight line path, the more resistance will be created to its movement. The roving is finally also moving forward. So, if I give more wraps, in that case resistance is going to be more, and therefore, winding tension finally is going to be more. So, these are EFG is for soft twisted roving, and HJK you see wraps are more, it is done for hard twisted roving, because we know the hard twisted rovings are basically a little stronger, they can withstand more tension, and therefore, I can make a very tight package, and therefore, we give 2 wraps around it. With that, we close this session, and thank you.